video. So hopefully that's okay. I dropped we did a sorting, right? The last thing we did, if you remember when we were all together, we did sorting algorithms. We did bubble sort and selection sort. There's two other sorts I wanted to get to, insertion and shell, but we got some sorting, so we're good. We're just going to throw those out. There's some unit testing stuff. Threw that one out. So today we'll get into linked lists, which really all we have left in this semester is linked lists, trees, 2 data structures, and then a couple small little things. That's kind of what we have left. You are, not that you can think about your next assignment, because this one is big and it's due this week, but your next assignment will be all about linked lists, and then your last assignment will be all about trees. So they'll be, right, I said that this assignment's a little bit harder, partly because you don't have as many examples to pull from. Okay. Your next assignment, you'll have all your linked lists. We're going to do linked lists for 4 lectures or 5 lectures, so you have all those examples to pull from. Trees, the same thing. So they'll be a little bit easier because you'll kind of know where to go. But I'll talk about the assignment 3 a little bit today at the end. So we're not going to get into insertion sort. We're not going to get into shell sort. But I was going to show you a video that just shows a bunch of different sorting algorithms. Remember, we watched some of those visualizations before. We'll watch one that does like 6 or 8 of them. And the ones that we know, we can talk about what they're doing. The ones that we don't know, then well, it's just fun to watch. Make sense? All right, and then we'll get into linked lists today. We'll talk about the assignment a little bit more. And then today's lab's easy because the part about linked lists today is really easy. So the lab today will be easy, and that'll give us some time to work on our assignment as well. I did make, if you're just so distraught that we're not going to do that second lecture on sorting algorithms, I made the lab still available, so lab 16 maybe or something like that, 15, but it has 0 points, and what that means to you is that it's extra credit. So if you want to do that lab, you can do it and get extra credit. Normally I don't have extra credit labs, so. Because I think insertion and shell sort are good algorithms to understand, so that's there for you. When I talk about the assignment, I'll tell you kind of what I've made extra credit on that as well. Do you have any questions? You guys look so happy this morning. Should have brought in my donuts or something. I'm a terrible teacher, I apologize. I always think about good things to do for my students like after the fact. Well, can't do anything about that now. All right, you guys ready? Mm-hmm. Say yes. Sure. So this first one's selection. So the name of the sort will be up here. It'll kind of tell you how many comparisons, how many array accesses it has as well. Because really, in a sort, right, we have to access the array in only 2 locations, and then we also need to compare, right, those places and possibly perform a swap, right? And so it'll kind of keep track of that stuff at the top. What you'll notice is that, right, because we know selection sort is slow, you'll notice that these bars are really wide. As we get to better sorts, you'll see that those bars get much smaller because it's not sorting, 100 values, it's sorting like 1,000,000 values. You'll see that it seems to go faster. So don't look at one video and be like, oh, selection sort looked like it took as long as, right, merge sort. Because they don't, right? Because the number of things that they're sorting are totally different. All right, you guys ready? If you get seizures, this may not be good for you. So let that be a warning. We ready? It's got some sweet sound to it. So let's see. Oh yeah, there we go.
Gee.
Because what does selection sort do? It finds the smallest value and then does what? Throws it in the front, right? Insertion sort, which you don't know. You would have known, but now you don't.
It's a lot of comparisons.
You take the next value and you move it down to where it's supposed to be in the sorted thing. So sometimes it goes all the way down, sometimes it goes all the way down a little bit. You notice the bars are a lot skinnier than even selection. Selection sorts your slowest one. Same sort as before, same name, but that's just a little bit different. This is the one built into C++. So if you use the built-in sort, this is what it does. It's a form of merge sort. If they're the same. This one's actually, sorry, I said the last one's merge sort, this one's merge sort. Shell sort, which is a quicker version of insertion sort. Try to be quicker, actually. I told you about this one, remember? Take two random spots and just switch them. And if you keep doing that randomly, eventually they'll be sorted. Right? Possibly, right? There you go.
I'm not seeing any sorting.
What?
I'm not seeing any.
Because it's not really, right? It's just, okay, let's just take this and switch them. And then let's take this and switch them. This is how you probably would write a sorting algorithm with that.
I just gave up.
It's sorted slowly. Right? It's like when you shuffle a deck of cards, eventually it actually starts sorting them back. Right?
So that's what the government workers use to sort their paperwork.
Exactly, right? Exactly. What's the high priority today? I don't know. Let's just take one from here and one from here. And there you go. Any questions on that? Don't get lost, right? They're kind of cool looking. Played the sound. You notice the only two I taught you were the only ones where the bars were super thick, right? Because I taught you the really inefficient ones. Because usually they're either efficient or they're what?
Inefficient.
Or they're easy to code.
Easy to code.
I like that. Maybe they're efficient or inefficient. Yeah, that's true. Usually they're either efficient or they're easy to code, but not both. You'll notice in some of those, it seemed like it was taking chunks and breaking it up and then sorting those chunks and then bringing them all back together. We do that through this idea of recursion, which we're going to get to here after linked lists. But this allows us to break up, basically do the same thing to different pieces of the data structure and then bring it all back together. Sound good? Questions on that? You ready for the new stuff today?
We're getting recursion today.
No. Recursion will happen after the next test. Well, yeah, there's still another test. Sometime. Before Thanksgiving, we'll have a test. And then we'll have a final. The finals week is now just a regular week, so we'll have an extra.
You have a test and one?
No, well, the final will just be a test. We'll have an extra day that week to do like inheritance or something. Whatever I threw out, I can bring back in. Oh, all right. We can do this. I think I remember how to lecture, so we're gonna do it. It's been over a week. It's been a while. So we're gonna talk about what a linked list is today, and we're gonna look at that by first looking at really the only data structure we know, which is an array. An array is really the only data structure we know where we store a lot of data of the same type altogether. Okay, linked list will do the same thing, store a bunch of data of the same type altogether. Trees, when we get to them, will do the same thing, store a lot of data of the same type altogether. They just take different approaches to it, and we'll see today why we have different approaches. Hopefully by the end of today, you'll realize that, right, arrays aren't the best for everything. Maybe you already know that if you've been doing your assignment, which you please tell me you have been. All right. Yeah, right? If I want to store a list of students' names, what am I going to use? The answer's there. Do an array, right? So code would look, right, if we remember how to write code, it would look something like this. Right?
Yeah.
What do we know about this array? Just from that snippet of code, there's some things that we know about it.
We know the type.
All right, we know it's type, right? So let's look at this. How big is it?
It's 3, right?
3, and will only be of size what?
3.
3, right? It has a fixed size attached to it. What does it hold?
Strings.
Strings, so it holds strings. Right, John is at where? 0, right? Index location 0. Jane's at 1, right? Each element is stored in what? In return, I'll give you a hint. Talking about memory, each one's stored where? Okay, good. Everything's stored in the memory address, but good answer. Good answer, good answer. What is that? It's like a game show, right? Good answer. Good answer. Is that Price is Right?
In the array?
No, I don't know what that is. Okay, good. It's in an array. But in relation to memory, right, where does John sit in memory, right? And where does Jane sit in memory? Where does Bob sit in memory? They sit next to each other, right? Because they're friends, right? They all sit in adjacent or contiguous memory. You'll hear, right, computer scientists say that, right? But a key thing about arrays is that everything sits in adjacent memory, right? So if we add in memory locations, and if we said strings took up 4 bytes, right? Then John at location 0 is stored here, and Jane's just right next to him, right? And Bob's next to Jane, right? Which is why, right, when we talk about arrays, we only remember the memory address of the first thing, right? We only remember this memory address, and then the square brackets and the index adds memory addresses to get us to where we need to go. Does that make sense? So arrays are stored in contiguous memory. This is also why arrays can't grow, because there's no guarantee that there's more contiguous memory next to your array to make your array bigger. Does that make sense? Right? So a big thing about arrays is that they're stored in contiguous memory. They have to take out a block of memory and say, this is for my array. Right? This block of memory is for my array. All right. Let's talk about adding data to an array. This is also going to help you for your coding assignment. Let's talk about adding data to an array. If you add data at the end of an array, or basically where there's extra space. So if we look at my array, right? If I have a 1 here and a 3 here, right? If I want to add at the end, and by end I mean kind of the end of where my data is in my array, so not the end of the array, but the end of kind of my list, right? It's pretty easy, right? If this is at index location 0, 1, I can just put something there. Make sense? Okay, but if I want to add something at the beginning of an array, what do I have to do? Move everything, right? Because everything's stored in adjacent memory, right? So if I want to put 8 right here, right? Really what has to happen? 5 has to move to where? 1 more, and 3 has to move 1 more, and 1 has to move 1 more, right? You have to kick people out. And every time you kick someone out, the next person has to get kicked out, right? So when you add to the beginning of an array, you really need to start at the end and start moving everything towards the end to leave room at the beginning of your array. Because there's no way to add more memory at the beginning or even in the middle, right? The same thing would hold if I added it here, right? 5 would have to move, right? The same concept holds. If you add it to anywhere but at the end of your array, you're always going to have to move that, right? You're going to have to shift it down the array. Does that take time? Does that take work? Yeah? Could you program it? You could, yeah. Right, once you program it, great. But you have to realize that once you program it, the problem still holds, that there is an efficiency problem. And whenever you add data to anywhere but the end of an array, there is time, and this linear time, because you're just shifting in things down, right? And there's a linear time complexity that says that it's going to take longer, right? It is faster to add at the end of the array versus at the beginning. You add at the beginning, it takes n amount of time, right? And when I say n, what do I mean? Size of my array, right? Because the array could be full or almost full, right? We know if the array is full, we can have that problem. You can't add anything. But if it's almost full, I have to move n things down in order to put my thing at the beginning. Does that make sense? At the end, if I add it at the end, it takes what we call constant time, right? There is no n, it's not linear, it's not exponential, it's just constant. However much time it takes to just add something to an array, that's how much time it takes. And at the beginning, you have that constant time, how much time it adds to the array, plus the end time. Does that make sense a little bit? So adding data to an array can be complex when we talk about efficiency. Because if we don't add at the end, things have to move, that takes time. Is it efficient for a small number of elements? Say yes. Everything's efficient for a small number of elements. If I have 10 things to sort, guess what? Bubble sort, which is super easy to write, and merge sort, which is not easy to write, are going to take about the same amount of time. Okay? Remember, things only get, when we're comparing like linear to exponential to constant, as n grows, right, then things get inefficient. So sure, for a couple elements, it's not a big deal, right? For this, it's not a big deal to shift 3 elements down. But for 1,000,000 elements, is it efficient? No. Right? Not at all. So the more elements, the more shifting, right? And that's where we get, right, the linear work, right? The amount of work is growing in direct proportion to the number of elements. Like, that's linear, right? Direct proportion.
Would you be able to tell the difference, like, as you're running your program?
I mean, there are ways to set it up so you can time things.
Oh.
Yeah, so you can do that. But what will happen a lot of times is that all of these algorithms, they've already been broken down mathematically, so you can just see, right, this is a linear algorithm versus a constant algorithm. Most of the work's done first, which is nice. All right, so if I were to add at index location 1, the number 3, what would I have to do? Shift what? Shift 8 and 2, right? And for integers, it's not a big deal, because I can just copy, right? Copying integers, that's not really a lot of work. Remember, copying objects kind of is a big deal. Right, but you'll notice that I really have to start here, right? Move 2 down, and then copy 8 over it, right? And so 8 and 2 have been moved, so now 3 can get copied into my array. Does that make sense? So you notice that you don't start at the end of your array. You start, right, at the end of the number of elements that are in your array. Right? We have that same concept in assignment 3. We have capacity of the array, right? That's how large it is, and we have size of the list, right? And that's how many, right, elements are currently in. So we always want to keep track of not only capacity, right, because things aren't always full, capacity, and then also size. Now, as we remove data from an array, the same thing happens. We remove data at the end of the array, no big deal. Right? If we remove data in the middle of the array, now we have a gap. Right? And we could just leave the gap. But really, the idea of arrays is kind of all the data gets filled from the beginning to the end. So we really need to keep track of that gap and remove it. Concept in arrays is called compaction. So compaction is the concept of, right, removing something from the middle of the array and then compacting down all the values to take up that gap. It works linear because it's just the opposite of what we were just saying. So if I deleted 1, right, at location 1, the 3 goes away. Everyone agrees? And then what happens? What has to happen? 8 moves down, and then 2 moves down, right? And then this spot, right, in an array like this, probably not a big deal. You just leave it, right? For your assignment, you need to null out that pointer, right? Because we're dealing with pointers. But theoretically, that spot needs to go away, right? But for an integer array, all the spots always have data, right? Every spot always has data. Right. We delete 3, which means we move 8 down, and then we move 2 over 8, and then we kind of lose 2. We kind of lose 2 by saying, right, there's only 3 values in my array, so I don't care about the other values. Does that make sense a little bit? So if I were to write compaction, which, right, how many people have written compaction for assignment 3? Anybody? A couple of you, right? Right. If you were to write it, which you need to write it, what are you going to use? Good, right? A for loop, some kind of for loop, right? Where do you think we should start our for loop? At the end? Well, what are we doing first? I'm taking out a number, right? And that's really what I know, right? I know that I want to delete at location 1, right? So I want to delete this thing. So then the question is, do I start here? Do I start here? I start where I'm deleting, right? Right? So where is I going to start? Int I equals what? Okay, so yeah, and this one's 1. Good, right? I'm going to call it position to delete. That way it works for everything. Right? But in this example, that is what? 1. Right? How far do I want to go? To the end of the list, right? Remember, and I'm going up. Right, I'm not going down, I'm going up. It's weird. Compaction moves everything down, but to compact, I'm going to start at where I'm at and grab the next thing and pull it down onto me, and then move up. Well, the next thing, pull it down onto me. Move up. Does that make sense? Right? So I go from there to what? Once again, Joel said what? The end of the list. End of list. Everyone good? End of list is not end of array. Agreed? End of list is the end of, right, the values in my array. Right? I'm just calling it a list because list is different than arrays. Right? And then I should go up by what every time?
1.
By 1. Question. Does that make sense? Yeah. And then what do I do? So let's think about my for loop. Right now, I is at 1. Agreed? So I is at 1, so that's 3, but I'm deleting 3. What did I do?
Just replace it with the next index.
Replace it with the next index, right? So how would I do that in code? The same my array is called values.
Value I plus
Does that work?
What if it goes outside the array?
Well, it shouldn't go outside the array. We should be okay. Will that work? Because the end of the list is at where? 3? Right? So I, which is 1, right, gets the value of I plus 1, which is 2, which is this, right? The 8 moves over. Then I becomes 2, right? And then I at 2 gets the value of
2.
this one, right? And then I becomes what? 3. But my thing ends because the size of right was 3. So I think
Oh, okay.
that might be helpful, by the way. I'm not going to erase that. That's one of the functions you need to write. Should there be some error checking around, like should that location exist and be in the array? Yeah, right. So there's some if statements you need around it, but compaction isn't too crazy, right? It's not too crazy. And then in the context of our assignment, right, that last spot, right, because now the list has gotten smaller, but that last spot, right, because everything is a pointer, this should be null, right? Set it back to null because we got rid of it. Oh, and because things are dynamic, you should probably delete the thing, right? You can't just copy things over, you should delete the thing at location.
Yeah, because that memory address still exists.
Yeah, right, we can move the pointers, but if we didn't delete the memory that that pointer was pointing to, then it still exists.
Yeah, so it'd be,
Which means that your program's gonna pass the unit test.
it's got a leak.
And then you're
though.
gonna lose points, because I'm gonna be like, yeah, it's a memory. Every call to new needs a corresponding call to what? Delete. Right? So that needs to happen at some point. So anytime you're removing stuff from a dynamic thing, you should always think, I should probably delete at least one thing, right? Because I'm removing something, right? It's going away. I create it dynamically, I remove it dynamically. So we looked at, right, shifting to add values to a list. We looked at compacting to remove values from a list. All right, other things that we might do with a data set, right, would be to add more things, right, and talk about the size. So if I want to add more space to an array, right, there's a couple different things that we could do. You can see the first bullet point. To add space to an array, I just make it large, right? Well, I might have 100 students, so let's make the array size 100, even though my class capacity is only 24. Right? But let's just pad it to make sure I never run into a problem where I don't, right? I have too many students. Right? That's what we did before, that's all we knew. Right? We're like, we don't know how many values we're going to add, so let's just make a large array. Right? Then we got to the dynamic, and we were like, oh, cool, I can ask the user. Oh, you only have 24 students? Great. I'll make an array of size 20. But right, when that 25th student shows up three weeks into the semester and, right, begs to be added to the class, what are you going to do? Right? Can you add more space to an array? The answer is no.
You gotta make a new one.
You have to make a new one. Right? So we can make it dynamic, and when it's full, create a bigger dynamic array. This is what you're doing in assignment 3. When your array gets full, and because arrays store values in contiguous memory, right? Once your array is full, you have to make a bigger array, copy all the values from your original array to your bigger array,
And delete the old one.
delete the original array, and now you have more space. Seems like a lot of work, huh? At least it's pointers, right?
Just pointing to a different place.
Right? So if I want to add capacity of 5 to my array, I can't just do that, right? This has been carved out in memory. It's in, right, contiguous memory, so they're next to each other, but there's not more memory for me to grab and put next to it. So I have to create a new array. I have to copy all the values from the old array to the what? New array. Notice, are they at the same indices? Yeah, right, because that all works. Right, and then what do we do to this array?
Delete it.
We gotta get rid of it, right? Delete that array. So arrays work. We've been using them a long time. They work, but they also have, right, problems. Right? They also have problems. Right? Let's look at your assignment real quick. We can dovetail this down. So your assignment is made up of a to-do list pointer that points to a dynamic array of to-do items, pointers, because they're dynamic, and those point to actual dynamic to-do items. And so initially, it looks something, right, like this. We're going to do 5 of them. So initially, it looks something like this. This is actually of type to-do item star star. All right, which makes that this of type what? Good, 1 star. To-do item star, right? And by default, they all start as what?
No.
No. When I say by default, I don't mean C++ defaults that for you. It means what?
You
And
got
when
it.
you create it, you should loop through the array and set every value to what? No. Okay, pointers, just like all of our other plain old data types, start out with garbage. Right? Garbage for pointers are what? Garbage for a pointer is just a random memory address. Right? I don't think your program should point to random memory addresses. Agreed? So we want to loop through that, we want to set them to null. Why is that the default? Because it's C++, right? Every language that came after that's like, let's at least set things to defaults. Like, let's set integers to 0, right? Because we count from 0 a lot. Let's set, right, pointers to null. But not C++. Remember, it's the manual car. By manual are like cars that have stick shifts. I don't know if you guys know what those are. That's what's automatics. Like, we just hit the gas pedal, right? And it goes.
Unless you're in park.
Huh?
Unless you're in park.
Unless you're in park. Yeah, that's true. That's true. I've been trying to figure out because C++ is the manual and most other programming languages are the automatic, but then like C is like even more manual than a manual, so I haven't figured out exactly what that is. It's the stagecoach. There you go, right? It's something like that. Yeah, you got to yoke up your horses and do all sorts of stuff.
Assembly running on foot.
Yeah, probably. Or walking, but
Crawling.
something like that. Does this make sense?
Yeah.
Have you done this at least, please? Tell me you have. If you haven't, don't tell me. Because I might ridicule you.
My imagination.
Remember all last week when you didn't have classes and you could have like worked on it?
I worked on it a little bit.
And I thought Chico sitting there hanging out, and some of you came and we got almost all done. My internet went out completely. Anyways. That's that. Add in your assignment's pretty easy because I'm not telling you to add at the beginning so you don't have to worry about shifting. Okay, add is the next available spot in your array, add a to-do item. Okay? Currently in my array, my next available spot is where?
0.
At 0, okay? Let's add a couple things. We're gonna add cap. Right? What's my capacity of my array?
5.
Right? And we're gonna add size. What's the size of my array?
0.
0. Okay. So we were saying that if I have a to-do item, right? If I have a to-do item, right? Lucky for you, you don't have to create the to-do item. It comes in as a parameter. The parameter is a pointer, so that is a to-do item. You just have to put it in your array. Someone says, hey, here, I've made this for you. Please put it and store it in your list. Okay, that's this. Right? Which means that it has some, right, item pointer to it. Isn't that nice? Don't you guys love pointers so much? Right, so it has an item pointer to it because it's a pointer, that's the parameter, right? The pointer is pointing to a dynamic thing. Okay, does this make sense a little bit? So this needs to go on my list, agreed? So I need to basically take location 0 and say it's no longer null, it's what? It's that. Does that make sense a little bit? Right? And then, right, when the function ends, the pointer goes away because it's made regularly, right? It follows scope rules. But your array now points to the first to-do item. Does that make sense a little bit? All right? How would I do that in code? What would I write?
Just say size. It goes to that, right?
Right, but first we need to start at my list because that's my array, right? My list at location 0 equals what? Item. Why do I say equals item?
They're both pointers.
Because item points to to-do item, and I want this to point to to-do item. Right? So I want my arrows to be the same. Assignment of arrows is assignment of pointers, right? Your array is made up of pointers. Item is a pointer. We just make them equal. Does that make sense? Okay, if I do that, then this is no longer null, right? This goes away. And I've added one thing to my list. So what else has to happen to my stuff over here?
Size increases by 1.
Size, right, plus plus, because size needs to become 1. Does that make sense? Okay, so here's the big question. the next time I add an item to my list, what location does it add in? Adds in location 1. What just became 1?
Size.
Size. Guess what? When size was 0, where did I add the first item? At location
0.
So what do we say? There's a correlation between what? Size and the next place in the array to add. Okay. I've seen students trying to do loops and stuff like that. You don't need a loop because size tells you where the next spot is available in your array. Does that make sense? So you always just add it at your list, right? Your array at location size, right? So long as what?
It's not outside the array, right?
Right. So long as it's not outside the array, meaning that so long as what? Capacity and size aren't equal. Because when capacity and size are equal, then my array is what? Full. And that's what we're going to talk about here in a minute. Right? So you can add so long as there's room in your array. Right? But once your array is full, right, then you have problems. So the next thing, right, the next to-do item is going to be added here. Right? We're going to point this to here. Null goes away. Right? It's the same algorithm no matter what. Right? Size goes up by 1. Right? You don't want to take a picture of that before I really destroy that thing? I'll give you a minute. Go.
So you were trying to find an item already existed in your array.
Uh-huh.
You have to create a new item and then assign the
You shouldn't have to create a new one because you're trying to find one that's already in the array. So if you're trying to find it based on like its name, right? You would just
on its location.
okay. So based on location, then if you know where it is, you can use restoration. Yeah. Okay. That was supposed to be off by 1 though, I think. I think human readable versus not, so that could be
I got that.
okay. Something else. Yeah. Questions? So other questions?
Right, so that would just be a function, you don't have to loop it. So you would just use.
Right, because every time you call the function, you pass it a new to-do item, and it just, right, it's going to add one thing, right? So the add item function always adds one item. We might call it 10 times, so 10 items would get added, but each one's its own distinct thing, which is why you don't do it.
So you would have to call a function, have an if statement to check if there's a spot available.
Right. Mm-hmm.
And then run through that.
Exactly.
And that's it.
And that's it. Right? And the beauty in what you're writing is that if there's not a spot available, you're going to add capacity. Right? And that's the next algorithm I'm going to draw on the board. So you're going to add capacity, meaning that you don't have to be like, if there's not room, don't add. It's always, if there's not room, add more capacity, and then there's always the code to add to the array. So that's just always there. And a simple if statement to say if, right? If not enough size, just add more capacity. All right, you ready to add capacity? Because this is going to all of a sudden look a lot uglier. Right? I'm going to add a third to-do item just because I think this will help. I'm making my to-do items small because I only have so much board space, but to-do items are made up of a string, an integer, and a boolean, right? So they have, right, things inside of them as well. But really, for our algorithm, we don't really care. Okay, you ready to add capacity? So we're going to say that it's full, and I want to add more, right, space to my array. We know that we can't just add space on the end of an array. Agreed? Right? So what do I have to do? We said we have to create a what?
New one.
A new one. Okay? Guess what? I'm going to call mine Tim. Because it's not going to last very long. Okay? What is the type of this Tim?
To-do items, 2 stars.
Right, good. So it's to-do item, star, star. Because it's a pointer to an array of pointers. Right? Remember, temp and list are the same thing. Okay? They both point to arrays. So they need to have the same type or you're going to have problems. Okay? So that thing is going to equal a new to-do item star of some capacity, and that capacity is going to be larger. Does that make sense? So let's make it larger. Right? Put a terrible arrow. Right? I made it 5 larger. Everyone good so far? So I made this new array, right? Basically capacity plus 5. I think for you, it's capacity plus 10. Does that sound right? Right, so your new array will be 10 larger than the old array, right? Please tell me this makes sense, that I shouldn't every time that it's full just add one more spot to the array, because then when I add one more, what's going to happen? I have to do it again, right? So I want to give some more space, right? That way I'm not constantly adding more, because this is all work, right? All this drawing I'm doing is actually work in the computer, right? So I don't want to do it every time. So you have to decide, right? How much do I want it to grow by? Do I want it to grow by 5, by 10? By 100, right? How much am I adding to this? I would also say that if your arrays need to grow a lot, then arrays are not the thing that you should use. And we're going to talk about that, right, when I get back to my lecture. Okay, what do I need to do now?
Make everything in the array null.
Okay, I can make everything in the array null. Good, let's do that. I just do this. This is also null.
Yeah.
You okay with
I
that?
was gonna say just write an end.
Are we good with that? Oh, that means no. I don't care. Okay, good. What's my next step?
Move everything from the old one to the new one.
Okay, move everything from the old one to the new one.
Probably a for loop.
Move is tricky, right? Because we say move,
Or a copy.
but we don't really mean move, right? Because we were working with pointers. So yeah, we're gonna copy arrows, but are my to-do items gonna move? No, which makes this more efficient than if they were, right, not dynamic, right? But I still need to do it, right? So I need a loop, right? And in my loop, I'm going to say my, temp at I equals my list at I, right? Inside of a loop. Okay, the loop should not loop through all of these, agreed? It should only loop through all of what? These, which is the current capacity. Notice I did not increase capacity yet.
So I is less than capacity.
I is less than capacity, good, right? And then temp at I equals that. So if we think about that, I starts at 0, we're saying temp at 0 equals list at 0. Well, what's stored at list at 0? This beautiful purple arrow, agreed? So what's now stored at temp at 0?
The arrow that goes.
The beautiful purple arrow. Right? It's no longer null. Okay? And then temp at 1 equals list at 1, which is another what?
Arrow. Beautiful purple arrow.
There you go. I will make you do it. All right? And then temp at 2 becomes this beautiful purple arrow. Are we with that? Now this is kind of interesting, right? 3 and 4 are what?
No.
Null. And so theoretically, these two spots that are null would be what?
Again.
Null. So you don't actually have to null everything out beforehand, right? Because that's a loop that would take time to null everything out. You can just copy everything over, and then you can start it where you ended and null everything out.
Yeah.
That's slightly more efficient. You don't have. I'm not going to dock you, please.
Minus 2 points.
All right. So I did that. Bless you. I did that. What's next?
You have to delete everything on the left.
Okay, I got to delete everything. They want to take a picture of this? Like I'm in the middle of an algorithm. I'm about to erase a bunch of stuff. You know? I don't have one of those cool smart boards where you could like rewatch it, you know. If anyone was wondering why assignment 3 is hard, I think I answered your question, right?
This seems time consuming, not hard.
A little bit of both. If you don't understand what the arrows are doing, or if you screw up the arrows in your code, right, that's where it gets hard. Right? All of a sudden you're pointing at something weird, your program crashes, you get no feedback, you're like, what's going on? Right? You should what? Stub out all your functions first and make sure it compiles before you write all your functions, and then write them one at a time.
Yep.
Okay. I told you I was going to erase stuff, right? So that should give you an idea.
You have to delete the first pointer pointing to that array and then delete the array.
You delete over here.
Yeah.
All right. So if I delete list, remember when you delete a pointer, does it get rid of the pointer? No, what does it get rid of? What it's pointing to. So if I delete list underscore, and I should be delete square bracket list underscore because it's an array. You don't want a memory leak, right? So I delete square bracket, list underscore, it deletes the array that list is pointing to. And the array that list is pointing to is this list. Make sense? That's okay because what?
Already have everything pointing.
I
to
have pointers over here, backup pointers, right? Because we never want to delete something that is a pointer because then we lose what it's pointing to, but we have backups. So if I delete my list, this lovely array, see, this is why I said take a picture, because it's never coming back.
It's gone.
All right, goes away.
We can rebuild
I
him.
erased a little bit, but yeah. What'd you say?
We can rebuild him.
We can
We have the technology.
Yeah, but I don't have the money.
We'll have the money.
$6 million man or whatever, I don't have that much money. Think about how expensive that person would be these days. The $1 trillion man. Or woman or whatever.
Yeah.
Everyone good out with the arrow pointing out because the arrow's still dangling out to them. Okay, so I did that, great. Right, I cleared up the old array space, but I still have the new array, okay? If my function ended, what would happen to temp?
That'll go away.
It'd go away, right, because it's local.
Oh, so
right?
list has
Remember,
to
my
be-
underscore variables normally stay, my not underscore variables, those are the things that go away every time functions. So what do you do?
So list underscore has to point to the new array.
So list underscore has to point to the new array. Okay, what's currently pointing to the array?
Temp.
Temp, that arrow. Remember, assignment of arrows is just what? List underscore equals
Temp.
temp.
And there you
List
go.
underscore equals temp, right? So the box list underscore gets the same thing that's in the temp box, which is this arrow,
Yeah.
right? And so this arrow becomes this lovely thing.
Ah,
Does that make sense? So before we said list temp at I equals list at I, right? Because we're dealing with what's inside the array. Now we're dealing with the pointers to the array. So now we just say list underscore equals temp, not temp equals list underscore, right? Because then temp would point to the garbage spot,
and then we would just have two arrows like
Yeah.
this.
right? And then here's a mistake that a lot of students make. They're like, well, he told me to always write delete things if I'm done using it. So they delete temp.
Oh,
What happens when you delete temp?
well, we don't know where that array is anymore.
Right, deletes this thing, right? Function ends, and this arrow points to what? Nothing. These things have nothing pointing to them, and I've kind of borked my program. Agreed? Okay. I called new, but I also called delete on my original list, so like my news and my deletes, they're even. Right? You always want your news and your deletes to be even. They're even, we're good. Created something new, but I deleted something old, we're even.
Well, since temp follows scope, it'll just delete itself when it goes
No,
out.
temp will get deleted,
Yeah.
but not what temp is pointing to. Remember, when you delete a pointer, it doesn't remove the pointer, it removes what it's
Oh.
pointing
Yeah,
to.
yeah.
Okay. So then, yes, when the function ends, right, scope goes away.
The pointer goes away, right?
Right. And now, right, to the outside user, what do they see? They see a list that has a bigger capacity, right? That has more room, right? All of the original things are still at location 0, 1, and 2. So to the outside user, they don't even know or care that a new array was created, right? All that hard work, but it's all hidden from the user, so you don't get any of the credit,
Oh.
right? To the outside user, they just said, right, add an item, right? You did all the work to say, I can't add that item, right, until I make a new array, I copy everything over, I delete the old array, and now I can add the item in. But to the user, it's seamless, right?
Yeah.
Yeah, right, yeah, if there's a time complexity that actually makes the program hiccup, yeah, then they're annoyed. Why like every 10th one, it just takes a little bit longer, right? But overall, it's seamless. Does that make sense? I'm not gonna erase that. That's kind of all the help that I wanted you guys to have on your assignment. Okay, remember the to-do items aren't dynamic, they should be easy. The to-do lists are dynamic, they should be harder, but not too hard. This is what they look like.
It's not that bad.
All right, let's get back on track. So arrays are good at storing information, agreed? They're a data structure, they store information well. They're not as great at doing what? What are they not good at? Growing. What else? Adding items to random spots in the array. Removing items from random spots in the array. Right? Because you have to compact or you have to shift up. Right? So that's where they don't work as good. Do they work? Yeah. For small applications like we're doing, are they going to work for everything that we do? Yeah. I mean, yeah. But not for large applications where we have millions and millions of data points. So we want something that's better at insertions. We want something that's more efficient for, right, at storing data in certain contexts, right? When we are adding a lot of values, when we are removing a lot of values, right? Let's find something that's a little bit more efficient, right? And that's where linked list as a data structure comes in. So this is a cool line, right? A linked list is a data structure that can grow and shrink dynamically, right? So it grows and shrinks dynamically. We don't have to add more values and remove, right, space and that kind of stuff, right? Once again, when you see the word dynamic, you think of what? What?
New.
New, right? Good. Which means that linked lists have to use pointers.
Yes.
Right? Because we have to use new, and we have to create stuff dynamically as the program is going. Right? So it's a dynamic data structure. Yay. Which means they're going to draw a lot more in the next couple of classes. Right? Linked lists are made up of nodes. So nodes are the structures that hold data, and then the linked list takes the nodes and arranges them in a certain way for them to work. You can think of nodes as like elements of an array. Right? So an element of an array which stores one value, right? A node is basically something that holds a value. But it's going to have a little bit more because it has to be a linked list. So in my example, they're going to hold a student's first name because that's what our original array held names as well, right? Linked lists in C++ are either a structure or a class, right? So it's either just data or it's the data plus all of the behaviors, right? So for us, we'll do a class-based where the class will know about its nodes and what they can do. The linked list class will know about, right, its list and what it can do. Right? So a big thing about these nodes in a linked list application is that nodes also link to other nodes. Okay, so let's say that again. Nodes of a linked list can link to other nodes, meaning that they have pointers inside of them, and those pointers point to other nodes, or they will point to other nodes. Kind of cool. They're all the same class, right? So, right, the node class has a pointer to a node class object, which means technically they can actually point to themselves, right? Because they are a node class, but we're going to arrange them differently. And we'll get a nice visual, right? So for a linked list, we just have all the nodes point to each other, and then the last node is going to point where do you think? A couple places it could point. Got a bunch of nodes that all like we're in a list together. The first one points to the second one points to the third one. The last one, where's it going to point? Okay, so there's two options. One is the first one, that's a circular linked list. So when you get to the end, you go right back to the beginning. Or where else could pointers point to maybe? No, right? The end itself, yeah. Like you got to the end and now you're just stuck in this little like, right, running around like a hamster on a wheel or something. Right? Do you love my conceptual representation of a node? Okay. Big thing. Nodes hold data, Bob, and they hold a pointer to another node, the arrow. Does that make sense? Right? And remember, our examples will be easy, right? They'll hold a string, an integer, right? But it could be, right, a string, an integer, right? This thing, that thing, right? So on and so forth, an array, right? They can hold whatever you want. Right? The key is they hold data, whatever that data is, and also a pointer to another node, right? That's what nodes hold. A folder? Yeah. Yeah, exactly. This folder points to the next folder. Right? How do we create a node in code? Well, it's not too hard, right? It has some private data and it has some public functions. Right? So the private data is the pointer to the next node, right? And then the storage, right? The string, what happened. right? And they can be single variables, right? They can be a single string, or they can be on lots of stuff, right? And in the public section, right, you'll have a constructor or constructors, right, to add data at creation time, a destructor if it's dynamic, right? Accessors and mutators to change the storage, right? And then you need a mutator to change the next node because the pointer in it, right, will need to point to the next node and you need access to it to change it. So these are all things that you'll see in today's lab that you'll create, okay? I said today's lab is easy, that's because you're not really making anything dynamic today, you're just creating the node. And then starting next class, we're gonna figure out how do I get my nodes in a line to point to each other. So today is basically like when you created the spaceship, right? You're just creating, right, a place to store data and a couple accessors and mutators, which we can do, right?
Yeah.
Yeah, so today's lab is super easy. But a linked list would look something like this, right? You'll notice that I have multiple nodes, in this case 3, that the first one points to the second one to the third one, and the third one to null, meaning the list is over, right? I've made it to the end. That make sense? So let's look at my linked list in relation to what I was trying to do with my array and see why I might do better or worse. So when I add data into a linked list, there's actually no need to shift nodes. All right? All you have to do is update a few links, which means that it just takes constant time to change those links. Okay? The leading is the same. I think I have a picture, that's what I was trying to get to. Right? So here's my exclusive club, Bob, Jane, and John, right? But Darla wants to be a part of the club, and we're gonna let her in, okay? So if Darla, and notice I put Darla between Bob and Jane. Everyone good with that? Right? But Darla can be added anywhere in my list, and I can add her in by just updating a couple pointers, okay? And I can do this because arrays are stored in contiguous memory. Nodes get created dynamically, right? Where do dynamic things get created from? Where in memory? Remember?
Heap?
The heap.
Yeah.
Which I said is just like a heap of memory, you just reach in and you can just grab memory, right? Who cares where it is, right? That's okay because each pointer, right, just points to a memory address. Those memory addresses don't have to be next to each other, right? It can be, right, memory address here points to a place in Chico, points to a place in Paradise, points to a place in Orville. It works, right? Because you just follow the arrow and it takes you there. And, right, there's no distance, so you're not driving to all these places, right? It's still instantaneous. Does that make sense? So if I was to add Darla into my list, what would I need to do? There's basically 2 main things I need to do. Change Bob's arrow to point to where? Darla. And change Darla's arrow to point to?
Jane.
Jane. Okay?
That's it.
And that's it. But in what? Reverse order. Why in reverse order? If Bob points to Darla,
We don't know where Jane is.
no one's pointing to Jane. Right? So there's an order to what we do, right? Right? And so really Darla, ooh, look at that animation. You guys want to see that again? Ready? Ready? This is what, you know, professors freak out. Right? Darla points to Jane, and then what? Bob points to Darla, right? So Darla points to whatever Bob was pointing to, and then Bob points to Darla, right? And we're going to learn that in code. So we're going to go through examples, not today, but next class on how to do that. Does that make sense? Did my list have to grow? Did I have to check for capacity or anything like that? No, right? Because we're just working with arrows. In fact, a linked list can grow to as big as the memory in the heap. Right? That's your limitation on size or capacity. Is I might run out of memory and then I can't add more things. But until then, you can have as many nodes as you want. No.
It just makes bigger arrays, right?
A little bit different. Because it was in arrays, because we were adding to the end of the array, or the end of the list, and so it looked similar. Yeah, but that was, we had to create a new array, loop through it all, right? So there's a lot of stuff going on. So there's no space limit, that's I was kind of hinting at, right? So let's look at the two structures. So to add to a linked list, it takes constant time, right? Constant time just means the work it takes to move some arrows, right? To add to an array, or how many people have used vectors? Anybody? I haven't taught them to you yet. Right? Vectors are built-in dynamic arrays that grow and shrink for you automatically, right? What you're writing in assignment 3 is a what? It's a vector. That's what you're writing. Okay. So there's always, no one asks me this semester, a lot of times students for assignment 3, right, there'll always be one that knows about vectors. Can I just use a vector? Because it makes it easier. Yeah. Like, no, you're writing a vector. That's what you're writing. So you can't use it. That's what you're creating, right? So they take linear amount of time. Why linear on insertions?
Because they have to go through the
Because you're going to move everything, right? And the only time it's not linear, it's constant, is when you're adding it to the end. Okay? Deletion, same thing, to remove something, and we'll go through that algorithm for linked list. Right? It takes a constant amount of time. You just delete a node and change some arrows, right? You're going to find that with lots of stuff. Lots of stuff with linked list is that you're just either adding something and moving arrows, or you're removing something and what? Moving arrows, and that's it. Doesn't take a lot of time. Arrays vectors linear because of compaction, right? I don't want holes in my array. I got to move everything else down. Okay. Oh, look, we've been bashing on arrays today, but let's talk about this. Indexing. Indexing is accessing an item, a value, right, at a location. Okay. Guess what? Arrays have indices, right? So for an array, arrays take constant time to get to anywhere in the array. If I want to get to location 5, I just say my array bracket 5. Bam, I'm there. Does that make sense? Linked lists, you'll notice they don't take constant time, they take linear time. Why do lists take linear time? Because they have to find it, right? Which means that if we go back, right? If I want to get to John, which is the fourth element, really, right? We would say location 3 for an index, right? To get to John, where do I have to start? Bob. We go from Bob to Darla to Jane, and then finally I get to John. That takes linear time, right? So when you're accessing lots of values in random locations, and I should say random because indexes basically say, okay, sometimes I need to get location 2, sometimes I need to get to location 98, I need to get there quickly. But when I'm doing a lot of different places, right, arrays are the thing to use because I can get to a place really quickly, right? So when I'm trying to access lots of data in random spots, arrays are where it's at. When I'm trying to get maybe all the data at one time, right, and I'm adding a lot of data and removing a lot of data, then linked lists become better. Because I don't need to get to John randomly, I need to get to all of them. Right, so it gets a little bit better. And then resizing, right? Resizing an array takes linear time. That's the algorithm we wrote on the board. And guess what? For linked lists, there's no algorithm because what?
This point
You don't need it, right? You just add pointers, right? Add something new, take some memory from the heap, and update some pointers. So there is no size, right? Capacity for linked lists, right? It doesn't exist. There is no such thing. You just keep adding and adding and adding because it's a dynamic data structure. It grows and shrinks what? Dynamically. Make sense? All right. Linked list disadvantages. Can't do binary search with linked lists. I think binary search is an algorithm we're supposed to talk about, so let's talk about it, right? Let's talk about binary search real quickly. Okay, binary search is the idea that in a sorted data structure, okay, it's actually really easy to get to where you want to go in that sorted data structure. And you know this, and I'm going to give you an example. Okay, if I say guess a number between 1 and 100, okay, some people will just say 6, 10, 100, 35, right? And let's say I'm going to give you multiple guesses, and I'll tell you higher or lower. Okay, what are you going to guess the first time? What's the best place to guess if you're guessing? 50, right? Because if I say higher, you've eliminated half of the numbers. If I say lower, you've also eliminated what? Half of the numbers. Does that make sense? And you keep slicing it in half again. So if I said higher, then you'd be between 50 and 100, and you would guess what? 75, right? So, yeah, right? 75. And then if I said higher, you would guess between 75 and 100, and then it gets a little bit harder. 87 or something like that. Is that right? 86, 87. Right, we know we have integer division in C++. When you write the algorithm, it just takes care of the half for you automatically. Does that make sense? So we just slice it, and eventually we get there. And it actually takes logarithmic time to do this. Logarithmic time is very good time complexity. Okay? Everyone good with that? Right? If exponential time is really bad, logarithm is like the inverse. Right? Really good. Right? And so to find something, regardless of if there's a million things or if there's 10 things, it's really fast to do binary search. Because you just slice it in half and half and half again, and you get there. It takes logarithmic time. It actually, right? Because if you think about it, with a million things, in one time you've eliminated 500,000 of them in one go. And then you've eliminated, what? 250,000. And then you've eliminated 125,000. And then does that make sense? It actually doesn't take that many eliminations before you get to the 1 through 100. But to get to the middle of a linked list, it takes linear time to get to the middle. And then it takes linear time again to get to the middle. So it's a lot harder. You can write it, but it's really hard.
It's not really required the size.
In fact, when we write our linked list, we'll keep track of size, basically how many things are in the list, right? But size doesn't really matter for a linked list. So I convince you binary search is really good, right? It's really fast, takes logarithmic time. There you go, you've learned something today. Okay? But it only works on what? When the values are what? Sorted, right? That's the key. So binary search is really fast when the values are sorted, which is why we have so many sorting algorithms to try to get values where we want, and then search becomes super easy. So sorting becomes really important because we already know the fastest searching algorithm. It's binary. Always will be the fastest, right? It's logarithmic because you don't have to look at every value, right? You could, at the very worst, a search would be linear, right? Is the first value it? No. Go to the second value. Is that it? No. Go to the third value, right? You would go to n values, and you would guarantee that you would find what you're looking for. But binary search says we can actually do it faster. You don't have to look at all the values in order to, right, find what you're looking for. Does that make sense? Sorting, you have to look at every value, right? Because you have to compare it. So it could be that the one value you don't look at is not on the right spot. Does this make sense? Okay. Linked list allow you to only go in one direction, right? First node points to the what? Second node. Second node points to the third node. So if you're at the third node, guess what? You can't go back to the second node. You only go where? To the fourth node, right? Once you go down. Until you write your next assignment, which is a doubly linked list where you have arrows pointing both directions. But it's more work because now you got to keep track of arrows pointing both directions. So all of our examples will be singly linked lists, right? They all go in one direction from the beginning to the end, and the end is null, right? Doubly linked lists, they go both directions, right? And we talked a little bit about a circular linked list where the last node points to the what? The first one. Right? So it's a circle. Where do you use linked lists? Well, a lot of times you don't actually use linked lists as their own data structure, but they're used behind the scenes for other data structures. All right, so stacks and queues, which we'll get to eventually this semester, you basically use a linked list because it's the most efficient way for it to do. Remember, lots of insertions, lots of deletions, not a lot of indexing, right? That's where linked lists become, right, important, right? Fast insertions, fast deletions, you don't really care about indexing. So if you don't care about random access, right, a linked list might be the thing for you. Does that make sense? Right? Remember, today's lab is just making a node, so there's nothing dynamic about it, although one of its members is a pointer, right? Because a node can point to itself, which means that one of its data items is a node pointer, right? Node star. Right? In your example, or in your lab, you're going to make a singly linked node, so your class is called SL node, right? Singly linked node. Which has one link, which is an SL node star. Okay, and it has, I think we're storing integers. So I think you know how to create integers in a class object. I think we could do that. Does that make sense a little bit? Okay, listen though to this. Just because you make a pointer today, you are not using new and you are not using delete. Okay, you are just making a data spot that can hold dynamic things, but we're not making those. We're going to let the list take care of that. So we have our nodes, that's our data stuff, and then we have our linked list, which is our manager class. We have a data class and a manager class. The manager class is in charge of making all my data things point where they're supposed to point. So today we're just making the data class. I can just hold that. So mutators, accessors, but not really doing much. Makes sense? Don't use new because then you'll probably have memory leaks, We don't want memory leaks. Okay, this is also really important. Okay, I think we're going to do 4 linked list labs. They all build on each other. So if you choose not to do today's lab, that's your choice. Okay, you can't do the next lab until you do today's lab. Okay, so better to do it and get the points for it than to do it and not get the points for it because you did it later. Does that make sense? So the same thing holds. So today's lab, Wednesday's lab, Next Monday's lab is taking Wednesday's lab and changing it. Okay, next Wednesday's lab is taking Monday's lab and changing it. Okay, so you need to stay up on the labs because otherwise it'll be too much, Because you have to go back and change. Okay. Grading is up to date minus assignment 2, but everything else should be up to date grade-wise. So please check that if something seems weird. Some of you, I'm thinking maybe you didn't. I'm hoping that you just forgot to push some of your labs up to GitHub. So please look at your grades. If you did something, just let me know and we can figure out where it is and why I don't have it. Okay? That make sense? You have questions? Otherwise, today's lab's easy, but that means you should still do it and get it done. Okay, assignment 3 is not easy. And the more you work on it today, tomorrow, and Wednesday, the more sleep I'll get on Thursday. The more sleep you'll get on Thursday. Because I'll go to sleep at a normal time, and you'll email me at 11 o'clock at night, and you'll be like, well, I was sleeping. I've been talking about this lab for 4 weeks. So. I made the UI extra credit, okay? So before it was, you're supposed to make the to-do item, the to-do list, and the to-do UI. There's 3 classes, 6 files. Okay, the UI is optional now, okay? So all you need to do to get full credit is to write the to-do item and the to-do list and have it pass my unit test, make to-do list or something like that. And when you type make, it tells you all your options that you can do. Don't even have to worry about the UI. You can just make the list. That's all I need. You don't need UI to run it, yeah. So if you just say, screw the UI, I don't have time, that's fine. But yeah, if you didn't do assignment 1 or 2, you might be like, crap, I probably should do the UI because I need those points. The people that always do extra credit are the people that don't need extra credit. It's just which is why I rarely offer it. Just sometimes learn. Okay, I'm gonna stop talking and start helping. Notice my talking was not helpful. This is what I'm assuming.
Yeah. Well, yeah, because you're gonna use string to build within that CSCI.
That's what I thought.
And then, yeah.
So, what, type this out, or the reality?
What's that?
Well, I have to type this out, or it's already like.
Oh, well, so what that actually is a combination of your to-do item.
I made one of them
description,
credits.
to-do item priority, and I think to-do item completed. So basically, yeah, it's like, this is the description, that is, that's your description underscore. 3 is your priority underscore, and 1 is your. So that's, and then you have to, yeah, you're using string straight to build, like, description underscore, arrow, yeah, you're not.
Yeah, I think that's what I do about.
All of them just replace looking for at signs and replace it with whatever. It's not, it's whatever this is, not tilde.
What's that? Well, I don't know about that. So that's what I assume it is.
That's what you use for the character.
I would probably just. Sometimes. That's why I said make new C++ files because I get smart. And I would probably just go in class examples. I'd probably go where we should first start talking about class. So we had this my class.cpp and my class.h. I probably just copy H. I was probably copy this CPP. That's like the structure you need. And obviously you're not including my class.h, you're including SL.h, that kind of stuff. But I think overall, we should just kind of be able to understand all that. Take the instruction. Here. Go like come in here and be like, okay, class name SL no, so just change the class name from my class to SL no, right? So on and so forth. Okay. think,
trying to restart my workspace because I was doing the get full.
Okay.
And then I had to run get full class master.
Okay.
Saying it created the file.
Sometimes you have to right click on like the PA2 thing here, and you can say refresh files, and sometimes they'll show it. Also, hopefully this will.
Yeah, because I added assignment 4 and I could see that I just couldn't see
Okay.
it.
Oh, it actually would. Do you think that if I added assignment 4, it would add everything else in?
Yeah.
Yeah, there they are. Okay.
I do.
I just want to try to move this.
Yeah.
So should this typically be the last?
No, maybe you want to do this short
What is that? Like, so typically, should I need to get there in my CCP?
I need to do it here. I'm okay.
We're just so short.
Yeah. So normally you can do short ones. If you do longer, it actually get less.
This one I commented out, because I actually did for this one.
Yeah, normally, you just need to.
That's, okay, I guess that's my question. So these are considered indicators, and even though this has like an arrow checking, that's like,
But they're technically called inline functions. They're actually, it's weird, when you write them in the H as opposed to the CPP, they're going to add it as something different. And short functions are actually faster.
well, I mean, is that something similar that should be done?
They're good, I mean, these all need to be turned out.
Oh, okay.
And they'll, the PDF will say like, return the
I was just wondering for the function to file, is it, like, has that, description and is, the next one, comma?
It's not comma separated, it's separated by accents. So that's why. So this is a description, that's the description, and accent is the
Yeah,
priority. and
and we use
accent.
the function to, filter out.
Just the description. Because the at symbol is a delimiter, and so if the description had an at symbol in it, like eat at 5 p.m., you can't put that in here because then the at symbol is going to mean 2 different things.
Okay.
So it's true.
All right.
Yeah. That's a driver. Drive me. Yeah. Which could be just a ring or something like that. So yeah, your test probably does it all, but probably will be something like, mine's an underscore and yours is an uppercase or something like that. But you don't need me. But I get Sean there too. I'll see you next week.
Yeah.
They just create the files.
So we just create the files and then
Yeah.
it's gonna be, like that's gonna be empty.
Yeah.
Yeah. Header folder.
And then I was telling people, if you go to cloud examples, and you look at like 10, you can feel like, because my class.h and my class.cp, they're just basic, separate compilation classes.
Okay.
So if you want to use those as the basis for what you're doing in here, it could be helpful.
Is it alright if I go, because I have to go print the questionnaires.
Yeah, and then eventually just give it a name. I just call mine like item. Oh, right, with all your brand, right? Because I mean, you can, to do item starts the type, so really that's like int. We still need to give it a name. I like to call it like item or item to add. That really helps my brain do it, right? Like, oh, this is the item to add. What am I supposed to do with it? Oh, I'm supposed to add it. That's right. That's what we're supposed to do.
Python does exactly what you say. C++ is, I don't work if it's not right. Python's like, yeah,
That's true.
this in here.
C++ does not to say fuck you a lot.
Yes.
I'm hoping you want to programming.
He's not. It's not. Not true. It is not true. Away from us. He hates us.
He's in the corner in a ball and playing right next to the something.
Usually goes to different rooms. I would say he goes to .ax is going to be your index.
Yeah.
I don't believe those, well, I'm not sure.
I was trying to make it so that when an I is on the certain, it's gonna pop through every element in the string.
Oh, yeah.
And when it gets to an element that's actionable, it replaces it with whatever this is.
Correct, yeah, so yeah, your for loop is going to,
I think it was .provide, and find the library I use it.
that is what I use, things like that.
Yeah,
Lower than less than string message. And open for those purposes.
they don't use the description.
No, because, no. Description is just a component. Or actually, well, I see what you're saying. Description is what you're performing the action on. But it's just being passed in. So I didn't write description. You don't have to. This technically is description being passed in. And then this string technically isn't like a description. I just didn't name it that way.
Is there a particular reason why you did it a variable?
put in Livestream. When it gets passed in, it's just description, but basically, yeah, I did Livestream. Basically, this will pressure I is smaller than whatever gets passed in outside. Other than using the index of the string is equivalent to that. Store that into that file.
Just pretty much I like the summer idea.
Yeah, I mean, I was.
I just couldn't remember what one not operating was.
Hi, Kevin.
Adios, guys.